All right, so today we started going over the section over finding initial velocity of projectiles. I'll tell you right now, we're actually going to cut this section pretty much in half. We're only going to go through example 1, and then you will not do practice problems 3 or 4. So that should help a lot. It just gets into some trig that's a little bit more involved than what I feel is worth us going through in this section. So when we're finding our initial velocity, we kind of have a pattern of projectile motion problems. We are able to figure out the same kind of steps that we can follow because we're pretty much just splitting our variables into horizontal and vertical components. And then we just set up our equations. The two equations that we use for projectile motion a lot are v equals d over t, and then d equals... Oh man, I forgot to write it down. D equals v1 t plus 1/2 at squared. Man, there's that. Oh, board, don't fall asleep. Okay. And then we can use a bunch of that to solve for any variable that we need, especially once we solve for time. So the reason these things are so simple is because we already know the initial velocity. So now we're going to solve for the initial velocity using all the other information that we're given. We're still going to use the exact same equations, and we're just going to combine them in a different way. So example 1, this will be the only example we actually are going to run through today. Find the magnitude of the initial velocity given the angle. How fast does a soccer ball need to be kicked on level ground and at an angle of 37 degrees above the horizontal to attain a range of 50 meters? So what that's saying is we got someone kicking a soccer ball. They kicked it up at an angle of 37 degrees, and they need it to go 50 meters. So what we're going to do here is actually rewrite let's go back here and set this up. We have our angle here to set up a triangle for our velocities. So we have velocity in the x and velocity in the y. Now we don't know what any of the v's are, but we need to kind of figure out how we can set this up. So we're going to just keep all the variables in their place. So let's say the cosine of 37 is going to be Vx over V1, and the sine of 37 is Vy over V1. So I can't solve for those right away. Having that information, I can rearrange them so that I can plug them into our equations to solve for something. So I rearrange it to solve for my Vx and my initial velocity in the y. And I'm saying initial velocity in the y just because the equation that we use for that section is going to be one that uses the initial velocity specifically. So I can lay out my variables for this problem. So I know that I'm moving 50 meters in the x, and that my velocity in the x is my initial velocity times cosine of 37. I don't know my time. In the y, the displacement in my y is going to be 0 because it starts at the ground, it's going to end at the ground. My initial velocity in the y is my initial velocity sine of 37. I don't know what my final velocity in the y is going to be. And my acceleration in the y direction is always due to gravity, so it's negative 9.8 meters per second squared. I don't know my time. So I have a lot of unknowns here that aren't really making it a whole lot easier, but I can create a way to solve for multiple ones at a time. So these are the equations that we start with. We already are used to seeing this guy. All that happened down below is I rearranged it. So I multiplied my time over, and then I divided by my Vx. So basically they just flip-flop places. So now I've solved for time because time is now something that I don't know. And then over on the other side, I just have my standard equation where my displacement equals my velocity times time plus 1/2 at squared. So we have an equation 1 and equation 2. And they're going to keep these color codings pretty much throughout the example to kind of help you follow along with what's going on. So we're going to substitute pieces in. When we start with our equation, we have both of our times that are unknown here. So we're going to put equation 1 into those spots because we already know that d of x is 50. And then we have a substitute equation for our velocity in the x, so that we are then left with only one variable we don't know. We're going to set that displacement equal to 0, too, because that was given in our problem. So once we filled in all that information, we actually have a pretty simple thing to solve for. Now, the way that they go through it is a little different than what I think worked out best for us in class. So I put this giant box here. But basically, this is the equation from that previous slide. I can cancel out my initial velocities in that first half because one is going to be on top of my fraction, one's going to be on the bottom. So they cancel, which means I'm only left with one initial velocity that's kind of just stuck in my equation. So I'm going to go ahead and kind of rewrite this and simplify it a little bit. 0 is 50 times the sine of 37 divided by cosine of 37 plus a negative 4.9, because I just went ahead and combined those, times 50. And I'm going to distribute my squared to each piece so that I have everything kind of separated and it's not dependent on anything else. So 50 squared divided by my initial velocity squared and cosine of 37 squared. Now, what you can choose to do is keep these pieces separated. What I think is going to be a lot easier for us is going ahead and condensing these down into actual numbers so that we can combine it all sooner and have less to kind of look at. So I'm going to take 50 times the sine of 37 divided by the cosine of 37. Oops. Hold on. 50 times sine 37 divided by cosine of 37. So 0 equals 37.7. And then I'm going to work on my second part. So 4.9 times 50 squared. I'm going to go ahead and just put the minus over here from my negative 4.9. So 12,250 divided by v1 squared, and the cosine of 37 squared is 0.6378, blah, blah, blah. So now I'm going to go ahead and simplify these two numbers by doing that division. So 12,250 divided by the decimal answer. So we have 37.7 minus 19206.1 basically over v1 squared. Now I'm going to move my 37.7 over. So negative 37.7 equals, well, here, I'm going to run out of space. So I'm going to kind of cheat it a little bit. So negative, oh, not blue. Golly, when did that happen? Okay. Negative 37.7 equals my negative 19206.1. Since they're both negative, I'm just going to change them both to positive because they're going to cancel each other out anyway in the math. And then I would multiply this over and then divide that back over. So I'm basically flip-flopping the position. So v1 squared is 19206.1 divided by 37.7. And then I take the square root for those. Square root that. V1 is 22.57, and that's going to be meters per second. So I think it was a lot easier to go ahead and put those numbers in and condense the numbers that we had, do the math up front besides rearranging our equations with our variables separately, and then going and doing the math. I'll show you, this is kind of what it turns into, and it's the same thing. You're going to get the exact same answer. It just, to me, looks messier, and it's a little bit more overwhelming to follow, but we still get the exact same answer. So that soccer player has to kick the ball with an initial speed of 23 meters per second to reach a 50-meter range. So the next set of examples was going to be finding the angle, and it was going to be using the double angle identity. I am choosing that we don't really need to cover this, especially at this time. So what I need you to do is go ahead and work through practice problems 1 and 2, which are going to follow the example that we just did. And then I'm also going to be posting the solving for acceleration in 2D because that is going to be a very similar set for you. That way we can try to finish this unit before finals. For those that are remote, let me run through how finals are going to work. First of all, you do need to go ahead and schedule when you're going to be coming in on the remote only time frame to be able to take your exam in person. This is unless you are quarantined, like officially. So the exam is going to be fully multiple choice. It is not going to be long form problems. It'll be shorter problems that we'll do practice on over the next week after we finish. I think relative velocity, we have 2 sections left, and then we will go through some review problems. It's going to be making sure that you understand how to put together the equations, how to solve some trig identities, and you will have an A, B, C, or D option for all of the answers. So you don't have to worry so much about doing these long form problems. I've said it before, and I'll keep saying it. Physics is supposed to be fun. It's been a lot harder to include a lot more of the excitement and entertaining parts of it this year because there's not a whole lot of labs that we can do in the time period that I'm given or with the restrictions that we have right now. But I don't want this to be something that hurts you overall. I want this to be just a prep class that if you take an intro physics course in college, you're going to be set. So these first 2 units that we've done are really setting that up. And then when we come back in the 3rd quarter, we're going to try to hit some more of the hands-on activity sections that we can do independently. And then 4th quarter, I will not be here. I'll be out on maternity leave. So that will be a strong build quarter. And I just wanted the remote students to be prepared for that. That is going to be something where you are going to be working more independently on doing engineered projects over different concepts that we have covered. So let me know if you have any questions. Oh, and now I won't be able to turn it off. There it is.